Okay. Today we still study section 2, and if we still have time, then study section 3. Take a review about some key points from the last class. Suppose we are given a table of function values about function f. Then the Newton interpolation polynomial that interprets this table is a polynomial of this form. Q0, where Q0 is 1. Q1 is x minus x0. Q2 is x minus x0, x minus x1, and so on. Qn is x minus x0, x1, x minus n minus 1. We use a different notation for the coefficients. For C0 only depends on function value at x0, so we use this notation for C0. And C1 only depends on the function value at x0 and x1. C2, the notation is this times x minus x0, x minus x1, and so on. Cn, the new notation is this. Cn depends on function values at x0, x1, and xn. Function value is this. We call this new notation divided. Yeah, these new notations, we call them divided differences. Yeah. There is a formula in the last class for a divided difference. The formula is divided difference that depends on x0, x1, x2, and xn is equal to divided difference depends on x1, x2, xn minus divided difference depends on x0, x1 to xn minus 1. We proved this formula in the last class. Xn minus x0, where the initial divided difference is defined to be the function value. Yeah, this is a function value at xr, function value at xr. Okay, now today, based on this formula, we develop a process to compute divided difference or to compute the coefficients of Newton interpolation. Yeah. Okay. Say for example, let me make a table. For example, okay. Assume for simplicity, assume n is 4. We have 5 roots. The first column lists the roots of x3, x4. Now, second column, divided differences of order 0. Order 0 means function value. Function value at x0, function value at x1, at x2, at x3, at x4. The third column for divided difference of order 1. This divided difference, we can compute it by this formula. Yeah. The computation is here. X0, X1. According to this formula, it is a divided difference and x1 minus divided difference as x0, then over x1 minus x0. And this is just the function value at x1, function value at x0. From function value at x1 and x2, by this formula, we can compute divided difference at x1 and x2. And from function value at x2 and x3, we can compute divided difference at x2 and x3. And from function value at x3, x4, we can compute x3, x4 divided difference. Now, the next column. After we get the second, after we get this column, then by the formula, we can compute divided difference at x0, x1, x2. And we can compute x1, x2, x3. And x2, x3, x4. Then the next column, after we get divided difference of order 2, we can compute divided difference of order 3, order 3. x0, x1, x2, x4, x3, x3, and x1, x2, x3, x4. Then finally, from these two numbers, we can compute this number. Divided difference is a number, x4, x4. The first row, the top row, the entries are the coefficients of the Newton interpolation polynomial. This way to compute the coefficients of a Newton interpolation polynomial, it turns out that very fast. How? Because take a look at this column. Take a look at this column. All the entries can be, all the entries, if you look at their formulas, this number only depends on function value at 1 minus function value at x0. And this number depends on function value at x2 minus function value at x1, then x2 minus x1. Because function values are available. Actually, we can compute the entries in this column at the same time. At the same time, right? So the time to compute this column, the time to compute all the entries we can compute them at the same time. Roughly, yes, the time to compute one entry, say this entry. This entry is only one division. So the time to compute all the entries in this column is roughly the time to compute one division. Similarly, if you write down the formulas for the entries in the fourth column, you will see that it turns out that we can compute all the entries in the fourth column at the same time, parallel. For this divided difference, the formula is x1, x2 minus x0, x1, then over x2 minus x0, also one division. So to complete this table, actually, look at the first row. Actually, we just need the time to compute 4 divisions. So if you use this table to find the coefficients of Newton's interpolation, the time is all the n. If you solve, if you find the coefficients of Newton interpolation by solving a lower triangular linear system, then okay, this is the time for this table. Lower triangular linear system. If you find the coefficients by solving a lower triangular linear system, because the solution of a lower triangular system is a sequential process. The time is all the n squared. N and n squared, the difference is huge when n is large. When n is large. This is actually, this table, this process is one order lower than solving a lower triangular system. For example, suppose to solve a lower triangular system take a few hours, say hours, take a few hours. Then by this table, in parallel to compute each column, then the time, one order lower. I can say that just a few minutes. Few minutes. So this is a huge difference. This is the first application of this rotation, dividing differences. Yeah. Okay. Let me show you one example about this table. Okay. Yeah. So that you can understand, you know, how powerful this rotation, dividing differences is. Okay. Take a look at one example. Say, example 1. Given this table about function f, the rows not necessary in increasing order. The first row is 3, second is 1, then 5, 6. Function value at 3 is 1, at 1 is 3, then 2, 4. Okay, now compare the divided difference table. Then write down the Newton interpolation polynomial. Solution. The first table, the first column of the divided difference table is the loops. The loops. The first row is 3. Second row is 1. Then 5, 6. Yeah, actually, I don't need this. I don't need that line. Okay. The second column, divided difference of order 0. That is the function values. Function values is 1, 3, 2, 4. The third column is divided differences of order 1. Order 1. By formula, it is function value. Function value at 1. -3, right? This number minus this number. Then over this root minus this root. 1 minus 3. It is -4, -2. So 2. Yeah. 2. Correct. So this is a 2. Yeah. Here is, we call the table. Here this entry is x1, x2. So it is the formula function value at x2 minus function value at x1. Then x2 minus x1. So this number is 2 minus 3. 2 minus 3. Then over 5 minus 1. 5 minus 1. So it is 5 over 4. So here, 5 over 4. This entry is this number 4 minus 2. Then over 6 minus 5. It is 2. It is 2. Yeah. Now the third column is divided differences of order 2. Here, this entry should be divided difference at x0, x1, x2 by formula x1, x2 minus f x0, x1, then over x2 minus x1. So it is this number 5 over 4 minus this number 2, then over x2 minus x1, minus x0, not x1. So x2, okay, this point is x0, x1, x2. So it is a 5 minus 3. The answer is -3 over 8. So this number is -3 over 8. 3 over 8. Okay. Now, this number, this entry is this divided difference. By formula, this number is this number minus this number. 2 minus 5 over 4. Then over x3 minus x1. Yeah, x3 here. 6 minus 1. So 5. So this number is 3 over 20. So put 3 over 20 here. Now, the last column. The last column compute the last column is for divided difference of order 3 or order 3. Yeah, order 3. Yes. This is an x0, x1, x2, x3. Yeah, order 3. So by formula, it is divided difference x1, x2, x3 minus divided difference at x0, x1, x2, then over x3 minus x0. So it is 3 over 20, yeah, this number, minus negative 3 over 8, this number, then over x3, 6, minus x0, 3, 6 minus 3. So the answer is 7 over 40. So this is the divided difference table for this set of function values. Now I can write down Newton interpolation polynomial. The first row occupies the coefficients of Newton interpolation polynomial. So therefore, the Newton polynomial, interpolation polynomial, is P. The first coefficient is 1, so 1. Then second coefficient is 2, so 2 times x minus x0. x0 is 3, so number 3. Then plus the coefficient, then times x minus x0, 3, times x minus x1. x1 is 1, so minus 1. And then plus the fourth coefficient. The degree of the polynomial is 3. 7 over 40 times x minus x0, 3. X minus x1, 1. Minus 5. Okay. So this is the polynomial that interpolates this given table. Yeah. This is a topic one. Topic one. In this topic, I introduce you a new process to compute the coefficients of Newton interpolation polynomial. This process very fast. The computational time is just order n. Okay. One order lower than solving lower triangular linear system. Much faster. The second topic. Divided difference properties. It turns out that divided difference, the concept is simple. There are only coefficients of Newton interpolation polynomials. But if we denote those coefficients in a notation, in this notation, it turns out that it has many nice properties. Okay, very surprising. Okay, now second topic. Let me present some properties. Topic 2. Property 2. The first property, all are theorems in the book. Theorem 1. The divided difference is a symmetric function of its arguments. Its arguments are x0, x1, and xn. Yeah, this property says that the order in x0, x1, and xn doesn't matter. Okay. Yeah. That is, okay. Thus, if C0, C1, Cn is a permutation of x0, x1, xn. Permutation, say for example, 1, 2, 3, 4. Switch some numbers, say 3, 2, 4, 1. This is a permutation of these numbers. Switch some numbers. If C0, C1, Cn is a permutation of x0, x1, xn, then we have the difference at C0, C1, Cn. This is a number. This number is equal to this number. In other words, the order in the logs doesn't matter. Okay. This is the first property. Now, the second property, theorem number 2. This property is about on the error in polynomial interpolation. Recall that in a theorem in one previous lecture, we saw that a function, P is an interpolation polynomial to the function. The difference is given by this. This is from a theorem in one previous lecture. Psi is some point times I from 0 to n, x minus xn. Yeah, xi, not xk. xi, right? Yeah. Here, this is the error by using interpolation polynomial. The difference between the function f and the polynomial is given by this. But now it turns out that the error can be given by finite divided difference. The formula is the new formula is here. Let P be the polynomial of degree log greater than n. Okay, such a polynomial, such interpolation polynomial is unique. Then interpolate function f at the loops x0, x1. Assume the loops are distinct, different. Then conclusion is, if x is a point different from the loops, then we have the following error formula. Then we have f minus p is equal to divide the difference at x0, x1, xn, and x. Here x is whole physics times I from 0 to n, x minus xn. Yeah, this formula this is a new formula. Okay, what are the difference between this formula and this formula? In this formula, we require function f has derivative of order n plus 1, right? But in this formula, the function doesn't need to be differentiable to order n plus 1. Here, this formula holds for any function. Yeah, this is f is any function. This function may not have derivative. Okay, yeah. So this is a big difference between this formula and this formula. Yeah. Property number 2. Property number 3. We will use this property in our later development. Property number 3. Theorem number 3. This theorem is on derivatives and divided differences. The theorem says that if function f is in this set, the function defines on the open interval a to b and has n plus 1 derivatives. And suppose the loops are distinct and also in the interval AB. Okay, then there is a point psi in the interval AB such that the divided difference at x0, x1, xn is equal to 1 over n factorial. Derivative on function f n times, then evaluate at the point psi. Yeah. if you plug in this equation here, if you plug in the equation here, then we will recover the formula here. Okay. But of course, in this theorem number 2, the function f is arbitrary function. Okay. Arbitrary function. Yeah. This formula, we will use it in Hermite interpolation, section 3, 6.3, 6.3. Right. Yeah, these are some nice properties about divided differences. This is topic 2. Yeah, we still have time to study topic 3. What is topic 3? Hermite interpolation. Yeah, topic 3. Hermite interpolation. Then what is a Hermite interpolation? Topic number 3. Hermite interpolation. Okay. Now the question is okay. Given a table, the logs assume they are distinct. Function value we are given at the logs given. And also derivative, some derivatives are given. Say derivative S0 given, second derivative given, and derivative order, say take derivative how many times? Say K0 is an integer greater than 1, greater than or equal to 1, minus 1 given. At the log x0, we have function value first derivative, second derivative, until derivative of order K0 minus 1, all are given. At the second log, we are given function value, derivative given, second derivative given, and then derivative, let me separate. And derivative of order K1 minus 1 given. K0, K1, they are integers. They can be different. Now, similarly, at x2, we are given function value at x2, derivative at x2, second derivative at x2, and until derivative of order K2 minus 1 at x0 given. K2 may be different from K0, K1. Okay. Now, last column. Function value at xn given, derivative at xn given, second derivative at xn given, and then derivative of order kn minus 1 at xn given. Now the question is, can you find one polynomial that interpolates this table? Okay, let me introduce an integer m. Okay, let K0, this is an integer, plus K1 plus K2 plus Kn. This sum is an integer. Let me denote it by m plus 1. In other words, m is this sum minus 1. This sum minus 1. Okay. Okay, now we want to find a polynomial, a p of degree m. A polynomial of degree m has m plus 1 coefficients. We want to find a polynomial of degree m such that let me take a general root xi such that p at xi is equal to function value at xi. Derivative of p at xi is equal to function derivative of function at xi, and so on. Derivative now this time derivative ki times derivative ki minus 1 on p at xi is equal to derivative of f ki minus 1 at xi. Okay, where I is from 0, 1, 2, and n. So this is our goal, to look for such a polynomial p. Okay, this polynomial at the roots matches with function values and also with derivatives. How to find such a polynomial? Yeah, this problem is called Hermite interpolation problem. Okay, okay, let's see how many conditions we are given. For xi, we are given one condition, second condition, corresponding to derivative of order 1. So this is the ki condition. So here in total, ki conditions. I is from 0 to n. So in total, K0 plus K1 plus K2 plus Kn. So many conditions. By this notation here, this is m plus 1. Right. So in total, we have m plus 1 conditions. Makes sense to look for a polynomial of degree n, because a polynomial of degree n has n plus 1 coefficients. So n plus 1 conditions perfectly determine m plus 1 coefficients. That's why we look for, we try to find polynomial of degree n to fit all these conditions. This is a Hermite interpolation polynomial. The first theorem is about interpolation polynomial. It is unique and it is existent. Okay, this theorem. Theorem 1 in this topic. This theorem says that there exists a unique polynomial P of degree at most M, fulfilling the Hermite interpolation conditions. Yeah, Hermite interpolation conditions. I mean, this M plus 1 conditions. Yeah. The proof should be easy, right? M plus 1 conditions completely determine one and only one polynomial of degree M. Polynomial of degree M has n M plus 1 coefficients. Okay. I think this is all for today. I don't have time to continue. Next time I present examples and also present a general method to find Hermite interpolation polynomial.